Some more to come. Okay, good morning. So, what we have seen yesterday or in the last few classes is about confinement, electron confinement. So, we have and we have seen the we found that this is 1.5, this is your EF. What we have seen interestingly is say T is equal to 300 Kelvin. So, Fermi energy is Fermi level is the level up to which electron occupation happens. It's a maximum field level at 0 Kelvin, and so at 0 Kelvin, the probability of occupancy of states below this level is 1, above this level is 0, but at elevated temperatures above 0 Kelvin, you have finite possibility of finding electrons in the higher energy states. And at higher temperatures, what happens to the probability distribution in the low energy states? So, it will go something like, okay. And what we have seen is, it is only within this energy range, within the energy range of kBT, the electrons can absorb the given thermal energy. So, this is your kBT, say T1. Okay. So, higher the temperature, more number of electronic states at the higher energy levels being occupied happens, is it not? Now, what it tells us is no matter what the temperature is, the probability of occupancy is always half. So, this is the reason why even for the conventional intrinsic semiconductors, we always show the Fermi level in the middle of the band, gap between the valence and conduction bands, just by convention. Okay. So, when you dope this system, of course, you have additional levels created. These are called the so-called mid-band gap states, and these mid-band gap states can give rise to interesting conducting and optical properties. Right. So, this is a very important factor. So, if T1 is 300 Kelvin, so if you calculate the kBT at that particular temperature, it is 26 millielectron volts. So, only 26 millielectron volts can be absorbed by the electrons, and these electrons of course are close to the Fermi level. Because I told you, if we have to account for a physical property like electrical conduction, for example. So, you have to make sure that the electrons move across the Fermi level. That is why when we talk about the electron velocity in a solid, it is always the Fermi velocity. These electron velocities are typically of the order of 10 raised to 6 meters per second. And when we talk about electron velocity, That means the electron must have made a transition across the Fermi level. Okay? So, since I called it EF, so now we can introduce this KF, which is the Fermi wave vector, and we can also introduce the Fermi velocity. Typical Fermi velocities are of the order of 10 raised to 5 to 10 raised to 6 meters per second. Okay? So, again, going back to what we have seen towards the end of the class, yesterday's class, is that in order that the lowest occupied electrons participate in a given process, right, you must provide that much of energy to make them free particles so that they can attain these Fermi velocities and then participate in an event rather, which could be a contribution to the process of conduction and specific heat, thermal conductivity, etc., etc. So that's the difference. That's the reason why now we know that not all electrons can participate in a given process. It's only those electrons within KBT, within that energy limit, participate in a given process. Okay. The next one is, yeah, so that's a potential well, and now it's very clear that we have so if I have the energy level separation and say if there is some transition happening, excitation of carriers to this level and say de-excitation leading to say emission in the visible range. Now what happens? As the particle size decreases, you will certainly see the energy levels separation, the separation between these energy levels changing. And once that changes, the same transition that you will see here between E1 and D2 giving rise to say H nu 1 will change over to H nu 2, and H nu 2 is obviously greater than H nu 1. And this is what we have seen. I've shown you an example of the so-called blue shift, where the emission property, if this emission happens in the blue spectral range, and you start seeing a shift towards green and blue, from red, green and blue. So the well-known blue shift happens because of with the carrier confinement, when energy goes as 1 by L square, when the dimension of the particle reduces, or when the box length reduces, you actually start manipulating the energy level separation distance. So it's as simple as that. So I have a larger particle that gives rise to say an optical transition, which you call it H nu 1. The same particle starts giving an optical transition in a different spectral range. Why does that happen? How do you explain? And this particle is again a pristine one. We have not doped it. It's the same particle whose size has been reduced. So what you see here is, this is a typical example of size dependent quantum confinement effect. Okay. Now, so you have all these discrete levels. Okay, what happens to this particle, this single particle, which is inside the potential well? This particle now, it's like it is confined between these two walls, these two boundaries, these two potential barriers. Okay, so it's like creating a node on one side, so that when the particle moves across, what you should observe is standing waves. And this is an example of how standing waves are created, okay, and you see that. Of course, these the standing waves result from the requirement that there is a node at the barrier edge, the node is there, and the wavelength of course determines the energy, right. Okay. Now you can also extend this to the three-dimensional case. Okay. Now you see, several events can happen when electron is confined in a potential barrier. Okay. One is when the electron reaches the potential barrier, one edge of the well, potential well, it can reflect back. Okay. And the second one is it can be transmitted. So this transmission is nothing but the tunneling effect. Okay. So it's like the electron, the so-called tunneling effect can be explained only by quantum physics, because classically when the electron comes to the edge of this barrier, it cannot make a progression to the other side of the barrier. But by quantum mechanics you can explain by what is called the tunneling process. Okay. In due course of time, when we see some of the applications, I'll tell you what are the implications of this the tunneling process. I mean, I gave you a brief introduction to what is meant by tunneling, and also I've shown you one of the very important applications of the tunneling process in the fabrication, construction of a technique called scanning tunneling microscope. It all depends on electron tunneling between two metal barriers separated by an insulating barrier. That's what happens here. Okay? And of course, you have these discrete electron energy levels, where you see the electron wave functions for n is equal to 1, 2 and 3, and the probability distribution in the case of the 3 levels. In one case you see the probability distribution in the case of an infinite potential well, and what you see on the right hand side is the probability distribution for a finite potential well. Okay. Where in the case of a finite potential well, there is a finite probability of finding an electron outside this box. Okay. Now, semiconductor heterostructures can be used to observe the quantum confinement effects. You know, I'll show you some very interesting examples. These heterostructures are nothing but thin layers of atoms or unit cells of different materials. Okay. And what are the applications of these heterostructures? We'll see as we go along. And these heterostructures, thin film heterostructures they are called, are normally grown by sophisticated thin film growth methods. We'll see those methods also. Okay. Now, one of the important points that I mentioned in the previous class is, so when you have these energy levels, discrete energy levels, you can have the, exactly like what I explained here. Absorption can happen. You can pump the electron from the lower level to the upper level, and the transition can happen from these upper levels back to the ground state. Okay. Since you have energy quantization, discreteness, the absorption process also will be discrete. So a given system can only absorb only certain energy values from the incoming radiation. That again falls back on the process of discreteness in the energy levels of atomic system. Okay. Now, so this is a single potential. You have a core there at the bottom, okay, here, and these are the various electronic levels. And as you can see, what we have seen in the last 2 classes is as you go up the ladder, the electrons tend to be more and more free. So this is the increasing binding energy towards the core nucleus, and the kinetic energy of the electrons goes in the other way. Okay? So the electrons become more and more mobile for higher numbers of n. Okay. Now we can easily write the potential energy of an electron at a distance r from a positive charge, that is the nucleus, that is the core, which is minus q by okay. Now, if you have a solid now, of course, now we have what are called the bound states. Now the periodicity is defined by the lattice. Let us say that all the positive core atoms, the core shell, are arranged in a periodic way. So then you see what is called a periodic potential, like what is shown here. Okay. Now it's a one-dimensional potential energy of an electron due to an array of positive charges q separated by distance a. Okay. Now this core exactly looks like this. A very naive picture is the lowest binding energy states can become free, to move through the solid, and the lowest binding energy states are the ones with the highest kinetic energy, and these are the states with increasing n value, larger n values. See, it exactly looks like that, the whole distribution, something like so you have the positive core there. You have these different levels. You can see that, the continuum is happening there, the energy continuum. You can also represent it in this way. This is a potential from the solid. Okay, and you have this, so I can call it with all these levels. The conduction, the valence band, and a conduction band. Now, well, in this case, of course, now if the electron moves in there across the Fermi level, when it moves inside the conduction band, you have the process of conduction. But is it confined by anything, or is it just free to leave the solid? No, it is not free to leave the solid. There is what is called, you have V conduction, V top. Okay, the top of the conduction band, the bottom edge. Okay, so there is a pseudo potential barrier created by what? It's created by the crystal surface, the crystal itself. So, see, we say that these electrons are filled in all these levels, right? You have the topmost field level, and the one next to it is the empty band, right? If there is a gap between these two, depending on the gap energy, you call it an insulator or a semiconductor. Now you can only move the charges across into the conduction band from the valence band by providing certain amount of energy. When that happens, this electron, of course, is confined to the entire the topmost unfilled band, which is the conduction band. It cannot leave the solid, because the solid itself brings out what is called a pseudo potential barrier, and this pseudo potential barrier is created by the crystal itself or the crystal surface. This is where again how this pseudo potential changes as a function of size reduction is a very important aspect. Okay, all right. Now, yes, so we have the molecule on one side, solid on the other side, you have the quantum particle. So again, going back to the range, you can make semiconducting quantum particles and quantum particles of metallic systems. All those fall in this range, and when you start seeing these changes in physical properties, and if you have a three-dimensional confinement in all three dimensions, you call it a quantum particle, and these particles are supposed to have dimensions in this particular range. Okay. Now, what you see there is LUMO and HOMO. This is highest occupied molecular orbital and lowest unoccupied molecular orbital. So instead of calling valence and conduction bands, it's also appropriate to call it the highest occupied molecular orbitals, the lowest unoccupied molecular orbitals, because you see the solid is normally treated as a giant molecule. It forms due to the formation of these molecular orbitals, right? So what we have dealt with is the way these molecular orbitals form, and the way this this formation ends up in the form of the bands in the solid, okay, and how these molecular orbitals behave when you have a small cluster within the range of 1 to 100 nanometers, and you have the giant molecule, which is a solid, and of course on the one extreme you have the molecular entity itself. So molecular entity per se is never a nanostate, even though that's the ultimate nanostate. But if you are looking at certain physical property changes, you must go on to the quantum particle level. Okay. Yeah. So we have this again. I go back to the same example of optical emission happening from CDSE, because CDSE again is a very simple system. If you make nanoparticles of cadmium selenide and get these nanoparticles in the form of suspension, colloidal form, what you see is depending on the particle size, you start seeing changes in the optical emission property. The color that CDSE macroscopic bulk emits is different from the emission that you get from the nano phase of CDSE, and this is a classic example of blue emission we have seen. That's because your particle size is reducing, so the energy level separation is changing, and that leads to change in the band gap, a classic example of change in the band gap engineering. And once that happens, the optically luminescing material should start showing spectral emission in different ranges, which otherwise is impossible to explain. It's only because of the change in the band gap and the separation between the electronic levels. And what you see here is again it's a simple experiment of absorbance versus wavelength, and you clearly see a change in the band edge. course, the band edges are not as sharp as what you would get in the case of bulk materials. If I take macroscopic bulk material CDSE, you get a very well defined band edge, okay? But in the nanoscopic form, you have the problem of surface defects, okay? And that sort of distorts the sharp band edge that you would normally see in the case of a bulk material. But what you see here is a clear indication of the shift in the band edge, which itself is an indication that size dependent quantum effects have set in this particular system. You understood? Okay. All right. So there is no other better example. I mean, this can be done at the lab level in a very simple way to show the effect of size dependent quantum confinement effect. There is no other better example than this, because CDSE shows optical emission in the visible range at 630 nanometers. It luminesces at the red spectral range, and this red emission starts shifting towards green and blue. A beautiful example of band gap engineering, blue shift, everything put together. Okay. All right. So that's what. So it's like you can play with the separation between these electronic levels, and playing with this separation means band gap engineering. And we can actually grow the two-dimensional nanomaterials that are quantum wells, where you have confinement along the thickness direction. So artificially grown quantum wells can give rise to the effect of band gap tuning. We'll see that. Okay, that's again the blue shift, well-known blue shift observed in, these are colloids of cadmium selenide, where when the particle size is cut down, the blue shift happens, and blue shift is because of band gap tuning, changes in band gap. And that you can see it experimentally on this side in a very simple experiment. Absorption versus wavelength tells you how the band gap is shifting. Again, I'll tell this probably 100 times. This is CDSE, macroscopic, also macroscopic. You take a powder of this. So macroscopic CDSE, also macroscopic, smaller in size. I powder it, and the powder particle size is say 100 microns, 100 to 150 microns. In all these three cases, the band edge should not change when I look at the optical property. But the powder, I further take the powder size down below 100 nanometers, and that's where you start seeing changes. So it's a perfect example of size dependent quantum confinement effect. Okay. Again, the same thing as what I have drawn there. We have seen this. So you have the atomic, the nucleus there, and this is how the band formation happens in a solid. And these top levels, this is where you have the free electrons. And if the top two levels overlap, you can call it a conductor. And if there is a separation between the top the occupied level and the next unoccupied level, and that you call it an insulator or a semiconductor, depending on the energy gap between these two levels or these two bands. Okay. Again, going back to the EK diagram, free electron parabola, and what we have seen with by applying the boundary conditions, you see these different zones. This zone, of course, we call it the zone between pi by a and minus pi by a is the first Brillouin zone. This first Brillouin zone is also called the Wigner size lattice. You can it plays a very important role. Which Wigner size lattice is nothing but the primitive cell in a crystal, and a primitive cell is a cell in which you can find just one electron, or one atom rather, right? One atom per unit cell is defined as a primitive cell, and Wigner size lattice is a primitive cell, and first Brillouin zone is your Wigner size lattice. Okay. Yeah, so at point A and B, you can find psi and D. This can be done. You take it up as a small homework and try to see how to get these values at point A and B, okay, at those 2 points. Okay. Right. Now you see. Now we need to see the way electrons are occupied in different levels. Okay. I was talking about this electronic density of states. What is electronic density of states? What information you get from electron density of states? So let's look at that concept of the modal density of states, or you can call it the electronic density of states in square well potential. So we need to look at the density of states for a macroscopic solid, a bulk material, and also how the density of states, if at all there are changes, right? In the case of the nanoscopic materials, the 2D, 1D, and 0-dimensional systems. Do you expect any changes in the density of states? Probably, no? Because unless the electron density of states are affected, you are not expected to see changes in the physical properties. So that means the change that you have seen with respect to the spectral emission in the case of CDTA or CDIC nanoparticles is something to do with the changes in the density of states. Let's see what it is. Okay. Now, the generic term dE represents the electronic density of states. Okay. It tells you how many allowed energy levels are there in a given range, of energies, say E to E plus delta E. Okay. Now, how does the density of states vary with energy is what we have to see, and the simplest case is we can start with the 3-dimensional square well potential. Okay. We go back to our standard relation. Okay. Of course, that's what you get there. K square, 2 ml square, because I have replaced K by n pi by L. So you have n square. Okay. Now you can plug in some values for this n. This n, of course, is as shown there. Is it not? Okay. So nx, ny, nz are the quantum numbers, and if this is a starting point, we need to look at how the density of states change as a function of energy. So how can we do that? These quantum numbers represent the allowed solutions of the wave equation, is it not? So how do we do that? Some of you must have done this. Most of you have done a course on condensed matter physics or solid state physics, is it not? basically, see, it's all about occupancy. If you just look at the analogy, very often we have a problem of defining what this density of states is about. No, it's just about occupancy. So, in order to understand this, if I start giving an analogy, probably you'll appreciate in a better way. Now you look at this. You know what this is, right? This is a Roman Colosseum, right? I've seen many of them. Roman Colosseum used for, why Roman Colossia are used? These are fighting arenas, right? So you see the, the bowl there. It's like the bowl in our open air theater with a very nice arrangement of seats, in this fashion. Okay, and that's what you see. So there are some areas where people are allowed to sit, right? Allowed to sit, okay. So it's about in terms of electrons, it's allowed levels, and the levels, the number of levels that are available to an electron, the number of seats available here, and how do you find the total occupancy is the question. But in the case of electrons, we can do it very easily because we have the Fermi-Dirac distribution function. Also, when electrons start filling these levels, they start filling in a very orderly manner. They won't violate Pauli's exclusion principle. Whereas here, when you go inside this arena, you see what happens. Now, this is the overall picture, and that's what happens. You see, there is no specific way in which these seats are taken. Okay. Now, if you look at the energy bands now, we know that the occupation happens in a very systematic way, and that leads to the formation of these bands. And you look at that now, just a small portion of this the seating arena, exactly compared with so the occupied and unoccupied states in the case of an atom in which these and then in a solid, you have the forbidden regions here, and these are the paths where no seating is allowed. Okay, so this analogy tells you now of course in the case of electrons you need to find out how to evaluate the total number of electrons that can be occupied in a given state. So how do you do that? So the ground state energy corresponding to Nx is equal to Ny is equal to Nz is equal to 1 is simply equal to, right, so 3 h cross square pi square by 2 ma square, and okay. So in this model what we require is at the boundaries your psi x y z should be 0, is it not? Because there is no electron found at the boundaries. So this requirement results in solutions that are, again, we have seen that that are standing waves, simply standing waves now in 3 dimensions. Okay. Now you see what happens if the quantum numbers are treated as continuous variables. It can be found that the number of allowed states per unit volume having energies between E and E plus dE will go something like that, right, is C times root of E dE, where C is 8 root 2 pi m to the power of 3 by 2 by h cube. Okay, we can derive all this, all right. So this function dE, which is equal to C root E is called the density of states function. Okay? Okay. Now, what can we do with this particular function? So, you have dE now what we need to get is at thermal equilibrium the number of electrons or the number of electron states per unit volume with energies between E and E plus dE. So, the actual number of electron states is given by Ne. Now, this Ne can be obtained very easily. You have dE there, the number of allowed states, right. Now, the total number of electron states within this energy limit E and E plus dE can be easily found, because now we also know the electron distribution function, the Fermi Dirac distribution function. So, if you know these parameters, we can get a complete picture about the electron density of states. Okay. Now, let us see what happens in the case of yeah. So, I substitute okay. So, here if n is the number of electrons per unit volume, so what is the condition required to evaluate n? Small n is the number of electrons per unit volume. N is the number of electronic states and small n is the number of electrons per unit volume. Now, I have dE, I have the distribution function. So, what you do is your n is integral 0 to infinity Ne dE, and you have the expression for Ne dE already. Okay. So, in fact, this condition can be used to calculate the Fermi energy. We have seen this, we apply the same thing like what we have done in this case. Okay. At E is less than EF, f of E is equal to 1, and E greater than EF, f of E is equal to 0, and at absolute 0, right, what you get is no. So, you integrate this between the limits of 0 and EF. Is it not? It's simple. This gives you now what do we understand from this relation? Of course, at T is equal to 0, your total occupancy is only up to EF, not beyond that, is it not? Now, in a similar way, what can we plot here? We have plotted between f of E, the Fermi Dirac distribution function or Fermi distribution function as a function of energy. Now, I plot n of E versus E. Ne versus E, how does it look like? That's your EF. It's the same concept that applies here. Now this is at T is equal to 0, K, absolute 0. Now as you increase the temperature, so this is your KBT. Again it's the same thing. Only electrons within that energy limit of KBT can absorb the thermal energy. So if T is 300 Kelvin, that much of energy can be absorbed by those electrons which are close to the Fermi level. Okay? And similar to what we have seen there, now if you go to higher T values, more number of electrons can go to higher levels. Okay? This is the representation of Ne versus E. Okay. Now, yeah, again we can go through the complete derivation process and get to this expression, okay, where EF is given by this relation h squared by 2m times 3n by 8 pi to the power 2 by 3. See, normally the complete derivation process we do in the regular condensed matter physics course. So I can help you to actually calculate these expressions. It's not a problem at all. So what is the average energy of a conduction electron in a metal at 0 Kelvin? We have seen that yesterday. Is it not? That's a big question always, no? You can calculate it now. What you require is N, and the Fermi energy typically for metallic systems ranges from 5 to 9 electron volts. That's the example we took yesterday. Remember, I said I have asked you to calculate the TF, the Fermi temperature corresponding to a Fermi energy value of 5 electron volts, just to see the enormity of this particular number. And what we have got was a temperature value of 10,000 Kelvin. And then we understood that in order that all the electrons in a solid become classical particles, attain Fermi velocities. In order to attain Fermi velocities by becoming classical particles, you need to heat up the solid to such high temperatures, which is impractical. All right. Now, this particular, so this simply we can just call it DOS, the density of states. Now, the density of states plotted as a function of energy, so it just goes as root of E. So for a macroscopic bulk material, the density of states varies in that fashion. Okay. Now this is interesting. So in any bulk solid, for any bulk solid, the density of states variation is root of E. And if you have done any course before on the physics of low dimensional materials, you will realize that if this macroscopic system is brought down in size, and the density of states will be affected. You will not see the same behavior for the submicron or nanoscopic scale systems, which are the nanosystems. So we'll see tomorrow how the density of states varies for 2D, 1D and 0-dimensional systems, and what are their implications. Obviously, from the example where we clearly see the the blue shift, band gap change, band gap engineering, it looks like the density of states has to vary as a function of energy when you cut the system down to the nanoscopic range. Okay, we'll see that tomorrow.